Okay, so this is a set of notes on how the graphs of f prime, and f double prime all relate to each other. Okay, so these are not unrelated graphs. Looking at one, you can get some data about the other ones and so forth and so on. So the first thing we want to look at is, how do I use f prime to talk about f, right? And how do I use f double prime, the second derivative, to talk about f? And there's like four major rules here, okay, that are all related. Oops, that's six, not four. Let's do four. Four major rules here that are all related. Okay, so you have two situations here. You have f prime is positive and f prime is negative. And you have f double prime being positive, f double prime being negative. So if f prime is positive, f is increasing. And if it's negative, f is decreasing, right? Because positive slope, we're going up. Negative slope, we're going down. Okay, f double prime gives me a sense of concavity. Okay, so concavity would be something like increasing faster or decreasing slower. In that case, I am concave up. So if the second derivative is positive, I'm concave up. So that means that if I'm increasing, the bowl opens upward. If I'm decreasing, the bowl opens upward. So I'm either increasing faster or decreasing slower. If the second derivative is negative, I am concave down, and in that case I'm either decreasing faster or increasing slower. So concave down as opposed to concave up. So this little reality here is kind of like the four pictures you need to know. So let's kind of go through that a little bit. Okay, so there's like four possible functional graphs. Yep, that's it, just four. Either you get this, which is increasing concave up. You get this, which is increasing concave down. You get this, which would be decreasing concave up. Or you get this, which is decreasing concave down. So this one happens when I'm f prime positive, f double prime positive, increasing concave up. This is when I have f prime positive, f double prime negative, so this is increasing concave down. So now I'm decreasing, so f prime is going to be negative. And concave up makes this positive, and decreasing in concave down is f prime negative, f double prime negative, right? So it's also noting that when you have the two signs being the same, like here and here, whatever it is that's moving is going faster. Because this one's increasing faster and this one is decreasing faster. And these two, where the signs are different, would be something slowing down. It's increasing slower or decreasing slower. So those are just kind of little tidbits that you can look for keywords, faster, slower, things like that. If it's faster, first and second derivative have the same sign. If it's slower, first and second derivative have the opposite signs. Okay, we can also use this slightly differently. We can say that f and f double prime can inform the f prime curve. Okay, so relative position for the f curve was unimportant. For the f prime curve, though, we care where the x-axis is. Okay, so the x-axis is going to matter here. Okay, so kind of thinking about this, we got, again, 4 rules, right? 1, 2, 3, and 4. If f is increasing, right, then f prime has to be positive. If f is decreasing, then f prime has to be negative. See, this is why we care about where the x-axis is. Now, if f double prime is positive, then f prime is increasing, because like f double prime is the derivative of f prime, so it acts like that. And f double prime is negative, then f prime is decreasing. So we're going to look at how this looks like on these 4 graphs. So that'll be our next move here. Okay, so again, there are 4 possible f prime graphs. Okay, so in each of these, we care about the relative position of the x-axis. So let's put those all in, right? So we have one where we're increasing and positive, right? So f, in this graph, f prime is increasing and positive. So this means that f itself is increasing because I'm above the x-axis, and f double prime is bigger than 0 because that's giving me positive. Okay, so this one is increasing and negative. So in this case, because f prime is negative, f is decreasing, but because it's increasing, f double prime has to be positive. Okay, so in this case, I could be decreasing and positive, but because I'm positive, f has to be increasing, and f double prime has to be less than 0, has to be negative, because the derivative is decreasing. And here I'm increasing, sorry, not increasing. I want to be decreasing and negative, right? Decreasing and negative, because I'm below the x-axis, because the derivative is less than 0. F is decreasing, but because the derivative is decreasing, then the second derivative has to be negative. So these are the 4 possible f prime graphs. Okay, so we're going to do a little bit of analysis with a particular curve here, and I'm going to use a tool called Desmos to show you how that works. Okay, so there's like this free online app called Desmos, and if you haven't used it before, it's really kind of neat. It makes doing some of this graphing pretty easily. So I'm going to go to www.desmos.com, and it says, boom, Desmos, start graphing, all of that. So I'm going to hit start graphing, and it makes this kind of space. And you don't even need to log in or anything like that. You can just start working in here. Now I have a very particular function that I've developed here. So we're going to call it f, and we're going to say that f is 1 over 20, and it's going to be times a whole bunch of binomials, x plus 2, x plus 3, and you can see like Desmos is over here shaping that thing as I'm going along, x minus 1, x minus 3, and x minus 5. Okay, so I did this one. I'm going to make that a little bit smaller. I did this one in particular. Let's make it slightly bigger. There we go. Because it's a nice 5th degree polynomial. It has a bunch of zeros. You can see how I shaped the zeros. I got one at -2, one at -3, one at 1, one at 3, and one at 5. So I kind of hit all the zeros. I put the 120 here so it doesn't stretch out too big. So that's my graph, okay? So we want to do a little bit of analysis from this. This graph is like increasing from -infinity, and then like if you click here, it'll tell you it's increasing until I get to this -2.572, and then it decreases until it gets to this like -0.558, and then it increases again until it gets to this like 2.053, decreases to here, and then increases back up. And the other thing I want to notice about this is that the concavity is down until I get to about here. And then it switches and goes up until I get to about there. Concavity's down until here again, and then up the rest of the way. So this thing switches both increasing and decreasing, so it switches direction and concavity. All right, so the nice thing about Desmos is it really will create the graph of the derivative in an easy way. So if I say d dx, that's take the derivative of f, and it's like boom, there's the derivative. Okay, so let's turn off the main graph for a minute. So the derivative is a fourth degree polynomial. That would make sense. The derivative of the fifth would give me the fourth. Now, what's critical here is noticing where the zeros are. Okay, so I have a 0 here, negative 2.572, one at negative 0.558, 2.053, and 4.278. What this means is that the direction of the main curve is switching at each of those places. So here, the main axis is increasing. Between here and here, the main axis is decreasing, back to increasing, decreasing, increasing. So I'm going to line the two graphs on top of each other, and just to make it easier to see, I'm going to make the derivative dotted. Okay, so the main curve is the red one, and the derivative is the dotted one, right? So now let's take a look. Where the derivative is 0 is where the main curve, so this thing is increasing until it gets to this value right there. And then, according to the derivative, it should be decreasing all the way around here, decreasing until it gets to that value. There we go. And then we're increasing again, so we're going to be increasing up until we get to the next 0 in the derivative, and then we're decreasing until the next 0. So the function from this point should be decreasing until we get to the next 0. There it is, right there. And then, because the derivative is positive, we're increasing the rest of the way up. So the first derivative informs me about increasing and decreasing. So when the first derivative is positive, the main function is increasing. When the first derivative is negative, the main function is decreasing. Okay, so we're actually going to bring into this the second derivative. Okay, so let's create another one here, and we're going to turn the first derivative off, and we're going to say take d dx of d dx, so that'll get me, nope, d dx of d, I don't want it to do that, no, let's put a parenthesis in there, of d dx of f, there we go. So this green function, I think, oops, there it is, this green function is now the second derivative, so I'm going to make that one dotted, right? So you can kind of see everything that's going on here. All right, so let's look at what happens here. So this should be informing concavity. So let's turn off the main function. So before this point, I should be concave down, then concave up until that 0, concave down, and then concave up again. So let's see if that happens. I'm concave down until I get to that 0. So yep, that's concave down. And then at that 0, I switch to concave up. And at this 0, I'm going to switch back to concave down. And at this 0, I switch to concave up again. So the second derivative is informing my concavity. So first derivative tells me whether I'm increasing or decreasing. Second derivative tells me whether I'm concave up or concave down. Now, the second derivative also says some things about the first derivative. If I look here, the second derivative is negative, which means in that area, the first derivative should be decreasing. Here, the second derivative is positive, which means that the first derivative should be increasing. Here, first derivative is decreasing, first derivative is increasing. So where the first derivative is increasing, then the main function should be concave up. Listen to that. Where the first derivative is increasing, the main function should be concave up. When the first derivative is decreasing, the main function should be concave down. So let's take a look at this. Okay, so here we're negative, so the first derivative is decreasing. We're positive, the first derivative is increasing, right? All the way to there, positive. Negative, the first derivative is now decreasing all the way to there, negative. And then positive again, the first derivative is increasing. However, we said when the first derivative is increasing, the main function should be concave up. Let's take a look at that. So where the first derivative is increasing, so from here to here, the main function is concave up. When the first derivative is decreasing, like here to here, right, the main function should be concave down till there. The first derivative is decreasing, there to there, the main function should be concave down all the way to here, right? And then the first derivative is increasing again, so where it starts increasing, the main function should be concave up. All right, so it's useful oftentimes to look at these graphs two at a time, but very rarely is it useful to see all three of them all on one page. So I think that one of the advantages of Desmos is it gives you the chance to see things change two at a time. Okay, so I want to briefly talk about points of inflection, and then we'll end this piece of notes. Okay, so there's a last little tidbit in this about graphs and things that are called points of inflection. Okay, in order for to have a point of inflection, the concavity must change. Okay, so it either changes from up to down or down to up. Okay, so it's going to change at some point, x equals a. Okay, so if it does that, then the point a, f of a, is a point of inflection. Now, places that you can find candidates, right? So you don't want to have to check every single point to see if it's a point of inflection. If you have a point of non-differentiability, okay, so if somewhere along the line the curve is non-differentiable, which note also if it's not continuous, it's non-differentiable, then you should check those points and see if the concavity changes. The other thing where this can happen is points where f double prime of a is equal to 0. Because in that place, you can also have a switch in concavity. Now, does it guarantee that you have a point of inflection when it's non-differentiable or when the second derivative is 0? No. That's where it can happen, but it doesn't always happen there. If it does happen, it'll be at one of these two places. But it doesn't necessarily have to happen there. You can have a second derivative be 0 and no point of inflection. The concavity doesn't change. So this just tells you where to start looking. So let's look back at our graph. Okay, so looking back at Desmos here, if I turn off the second derivative, I get some semblance where concavity is changing. somewhere here I'm going from concave down to concave, I'm concave down all the way until around here somewhere, right? And then I'm going to be concave up until around here somewhere, and then concave down until around there, and then back to concave up. Now, let's take a look at the second derivative. If I bring the second derivative back in, there it is. So like at this value of the second derivative, right, that's where the concavity is shifting. The concavity, let's turn that one off. The concavity is shifting when x is negative 1.772. And then again, the concavity is shifting from up to down at 7.61. And again, the concavity is going to shift when x is 3.412. So it's going to go from down to up. Now, so those are three places where the second derivative is 0, and in all three places the concavity shifts. Okay? It doesn't have to shift when the second derivative is 0, but if it does shift from up to down, either the second derivative is 0 or there's a point of non-differentiation in the graph. Okay, so there you have it, a little bit on f double prime, and f prime, and a little bit on points of inflection, and we'll work with it from there. All right, so thank you.